Hi everyone, welcome to today's webinar on inline color measurement and closed loop color control in the white paper industry. I'm Robert Grotans, the Global Technical Marketing Manager at X-Rite, and I'll be moderating today's webinar. Presenting today is Manfred Binder, our Sales Director for Inline Color Measurement. I'll turn it over to Manfred to kick things off.
Hello everybody. Today we talk about color measurement in the white paper. But first of all, I want to show you why is it so important to talk about color. I mean, this is now packaging, but if you look at these boards, you have one staple of different boxes, and obviously they have all different colors. So which box would you pick? Which one is the right color for you, or which you think about has the right content? Or if you look at these boxes, always a small and a big one should come together, but the package has a different color. Would you like to, or would you trust in the content of the boxes? Look at these folders. They have all different colors. Does this be a high quality for you? So I think this is really critical. Everybody can see differences in the color shades. So this is why we say color is a primary quality criteria. And today we talk about white paper. If you look at that book, all these pages have different colors. Why? Because there is different optical brightness inside. They have different shades, and from each package of pages is made from one different reel. If the reels have not the same color, you see different colors in the book itself. So this is why we say color is very important. If you look about what causes these color changes in the paper. So if you make paper from recycling material, of course, the raw material, the recycling material has different shades. Today you get a red paper as a recycling material, tomorrow yellow, bluish, whatever. All these different shades go to the paper machine, and at the end you should produce a white paper out of it. If we talk about the fillers, if you look at clay, calcium carbonate, if they come from different mines or different locations, even in one mine, the shade of the fillers are changing. So we have to adjust the color accordingly to these raw materials. If you use additives like retention agents, like fixatives, the more you use, the more color goes to the fibers, the shade will be different. The pH value of your paper will influence the color. And of course, if you dilute your dye stuffs, you will have different concentrations, and these different concentrations will also influence the color of the paper. So all the raw material at the beginning of the machine is different. It has different shades. It can change during the production, but at the end, you should have one stable color on the machine. And this is what makes it so complicated. If we talk about color measurement, it's not only the color we measure. Sure, for some papers like laminated paper or kraftliner, there is just the color which counts. But if you look at newsprint, tissue, or if you look at graphics paper, coated paper, or offset paper, these are thin papers where we also have to measure the opacity. If you look at all white stuffs, like white cardboard, graphics paper, coated paper, offset paper, of course, whiteness and brightness is important as well. So all these parameters, what you see here, we measure with our system, and we call it the color measurement. I have written here that we have 700 successful installations in the paper industry. That means it's a successful installation. If you know somebody who is using our system, you can call him. Everybody which we have, which is using our system, is happy with it. Doesn't mean that we do not have problems. Of course, it could also be a problem with our system, but we solve it quickly. In total, we have over 1,000 installations. So you see, our main market is the paper industry. Just 300 installations are out of paper. Why do we make an inline color measurement? So, of course, the inline measurement gives you early results of the paper. This helps you to shorten up your startup time and to have a much quicker shade change time. Typically, you can save 50% when you go from a certain color to another color. Or if you start up and you start your dyeing process, you can save 50% of the time. If you save time, you also reduce the waste, typically by 50%. You can react immediately if there is something on the machine. So if you see that the paper goes away from your target, even before you are out of spec, you can adjust something on the machine and the paper comes back to the target. So this helps you to have a constant good quality. We do have a documentation of the entire production. This means if you have no inline color measurement, you can control only the end of the reel. So that means the end of the reel and the beginning of the reel is quite okay, but you don't know what happens inside of the reel. Some customer complain and say, you know, the beginning and the end of the reel was fine, but in the middle there was a color deviation, so we have to reduce the price. If you have the full documentation, you do not have to reduce the price because you can prove that you have a good quality. And of course, only with the inline color measurement, you can make a closed loop color control. If we talk about the system for color measurement, it's not only that we sell a kind of spectrophotometer and we give you a piece of software and say, help yourself. We have a whole frame which is mounted into the machine. So that means this frame is customized to your machine. It's tailor-made. We built something that fits into your machine. This frame also moves away. So we have a frame control box over there to move, to swing everything away that you can easily feed up the new paper if you start the machine or if you have a paper break. Of course, we do have a power supply with external signals. The connection from the instrument to the computer could be up to 500 yards. It's a CAN bus signal, but we have a box very close to the computer which converts the CAN bus to a USB signal. So you can use a very regular computer. It just needs to have a USB port, and then we can connect everything to our instrument. If we talk about the closed loop control, of course, we need also to connect pumps which are also far away. They are somewhere in the dyeing room. And we can connect external signals like a DCS system. So this is the full system what we are talking about. It runs independently, so you do not have to do anything from that. We will set up everything. Let's have a look at a paper machine. So this is a very simple paper machine. You have a chest, you have a fan pump over here, which brings the pulp onto the screen section. So you have the screen section over here. You have a press section, a drying section, and a reel up. So this is a very, very simple paper machine. The first position where we can measure the color, it's in the pulp. If you talk about the pulp measurement, unfortunately, the values which we measure over here do not correspond with the finished paper. Here we measure the water, we measure everything which is in the pulp, fibers, pigments, dyes, whatever. But we do not know how many pigments or how many dyes are fixed to the fibers. So the color measurement is a little bit different than the finished paper. Typically it's darker. But if you have a change in the pulp, for sure you will have a change at the finished paper. So this is a kind of, we call it an early warning system. If you see a change over there, you should be aware that there will happen something on the machine later on. But you can see it even before the pulp is on the machine. And of course, at this position, the optical brightness can be measured as well. It's an early warning system. We call it an early warning system. What we do is we have a U-tube over here. So the pulp goes in here through a bypass, it goes out here, and through the design, there is a glass window over here. The glass window always stays clean. So this is very, very easy to use. How do we use it? For example, we have a pulp over here. And so one pulp line is over here, which is the clean pulp, let's say, and this is the waste pulp. So you can mix up both of these lines, pulp lines, to have a certain color over here and to keep it constant. You can maximize the waste pulp or the not so clean pulp which is typically cheaper to achieve a certain color and go onto the machine. Or a second possibility would be, if you have a mixing chest, if you put in the colorants by hand, you can see if each batch has the same color than the next batch. This is how it looks like. So it's just a box, and you see there is the incoming pulp, and there the pulp goes back through a bypass, and this is mounted typically directly onto the chest. So this is the first possibility. It's an early warning system. The most interesting part is over there. So we measure right before the reel up. At this position, this is the most used location. We have a very good correlation to the laboratory. So typically we say if you have an instrument in the laboratory, this is the leading unit. The laboratory is always right. So we take even the standard values from the laboratory and put it to our system. And then we correlate our measurements, correlate the measurements from our system to the laboratory. And of course, at this position, the optical brightness can be measured as well. Here we have some pictures. This is a video. I hope you can see it. So the machine runs, and you see the instrument is swinging in. Typically position, we are always very close to the scanners right before the reel up. This is the measurement. This is how the software looks like. I will show you later on what these values mean. You see this was a paper break. So after the paper break, we start with the system. First measurement was a little bit too dark. Then it goes up immediately. You see how they feed the fresh paper. When the paper is stable on the machine, we get a signal from the machine. And now the instrument swings down, and this is typically the same when the scanner starts to run. There is a background arm over here. And now we have the first measurement already. So this is from a different position. And you see we measure with non-contact, only the background arm is touching the paper. So we were asked many times, why do we make a single point measurement and not a cross-direction measurement? Most of our competitors offer a cross-direction measurement. A single point measurement is a real advantage because you have only one color on the machine. So you put the colors into the chest or into the pulp at the beginning. If you mix it up well, there is only one color of pulp going onto the machine. You have no chance to say, please, the blue pigments go to the right-hand side and the violet pigments you go to the left-hand side. It's just one color. If you have a color profile on the machine, it's not really the color which is different. It's all the other parameters which are influencing the color. So if you have a moisture profile, of course, this will influence the color, and then you have a color profile too. If you have a thickness profile or an opacity or a temperature profile, all of these profiles will influence the color measurement. So this is not what we like to see, because if the let's say if the moisture is wrong, we do not want to correct the color because the moisture is wrong. So we need to have a stable measurement which is nearly independent of the moisture. And even if we talk about white paper, if we talk about the coating machine, here we have the same problem. If you have a coating on the machine and you have a profile on the machine, it's not necessarily a coating profile, it's maybe just a moisture profile. So it doesn't make sense to adjust a coating on the color measurement in cross direction. Then it's better to make, for example, a moisture measurement and correlate to the coating process. But the coating color itself, it's better to measure on one side. And I show you this in the next slide. Or to show you this, I need to explain a little bit more what we do. If you measure in the laboratory, typically you take the paper, you fold it together, and you make an infinite layer measurement. We cannot do this on the machine. We cannot fold the paper, so we have only a single layer. What we do is we measure the color with a white background, and you see this is the spectral curve over here. So maybe I should explain, this is the visible range. So the visible range goes from 400 to 750 nanometers. We have the UV range over here, and this is the reflectance curve. So we measure over white, and we have this reflectance curve over here. And we measure over black, and as the paper is not totally opaque, the reflectance curve is a little bit darker. We get the reflectance curve over here. And then we do a calculation and we calculate how the infinite layer look like. We calculate how would the paper look like if you fold it together. And you see, then we get something over here. And this is not just an average between two curves. This has to be calculated depending on the values over white and over black. So we need two measurements to calculate the infinite layer. If you want to measure also the optical brightener content, so base whiteness and optical brightener whiteness, you need a third flash because these measurements are done without UV, and then you need to have a third flash which shows you the content of the optical brightener. So let's go to the next slide. This is here a paper web which runs in this direction. And for example, moisture reasons or whatever, we have a disturbance here in opacity. So the paper is 5% less has less opacity than over here on that spot. So if we make a measurement on one side, we measure over here, first measurement over white, second measurement over black, and we get a certain set of LAB values and opacity over here. So this is correct for this spot. If the color is wrong, we can make a correction because it's the right color measurement. Let's say we have a traversing beam. So if you make the first measurement over here, and then the instrument moves and the second measurement is over here, then we get another set of LAB values. Unfortunately, this is wrong because it's caused of two different measurement spots. If you would have a closed loop control, you would immediately reduce the colors because you are too dark. And this is wrong. The color is okay, just the opacity is wrong. So it's, now you can say, of course, what happens if you measure right in here? If you measure right into this disturbance, it doesn't matter because then you have the right color values, but it shows you that the opacity is wrong. We make our color corrections only on the LAB values, not on the opacity. The opacity for us is just a leading indicator how to calculate this infinite layer. So a measurement in just one direction, in machine direction, is much more stable than a cross direction measurement. Here I have again some more pictures. So this is an instrument, it's unfortunately the old unit where we measure transparent paper with an opacity of only 20%, including optical brightness. So this is a very difficult measurement, but we can make it very easy and we have an excellent correlation to the laboratory. Another instrument, so this is now brown paper, and you see the instrument is mounted here with a different kind of frame. Also a very typical installation, very close to these scanners. We do have a special scanner for, typically we use it for security papers, but also sometimes for white papers. So this can be adjusted in cross direction. The reason is only if you have different width on the machine of paper. So if you have a very small paper and a very wide paper, then you can adjust it over here. Or in the security paper, if you have watermarks, then you can make the measurement in between the watermarks. If you would be measuring on the watermarks, we would have the same problem like I explained before if you make a cross-direction measurement, because over white you make, for example, the measurement on the paper, and over black you do it in the watermark and you get completely wrong values. And the last, one more picture of this. This is a Gemini measurement. It means we measure top side and bottom side. In white paper, it's not used that many times, but especially on brown papers where you have different layers, we can make a closed loop control from both sides. If we install a system, it typically looks like this. It's very clean and very nice. But if you come back after some months, it looks different. So for example, this is a system which is installed in a tissue mill. A tissue mill is really dusty. And you see, you can hardly recognize the instrument. We have here the measurement spot, and you see the measurement spot is closed when we are not measuring. So this is now in park position. There is no paper on the instrument, and this is the reason why you can see this opening here. During the measurement, the lid swings away, and we have an airflow going in, and it keeps the optics clean. So even when the instrument looks dirty, the optics is clean, and we can make a very safe measurement. In the white paper industry or in many other industries, it's enough if the instrument is cleaned once a year through our service technician. Sometimes we recommend the people to do a cleaning also at the, how can I say, at the service intervals. So you should make an external calibration every 6 weeks. If you do the external calibration, just clean it a little bit inside. It's not a rocket science. It's just one screw which needs to be opened. Then you can clean it. You do the external calibration all together, including bringing the white standard to the instrument and bringing it back. It's maximum 30 minutes. So these were some pictures of the instrument. And of course, we have a software. Our software shows up to 6 trends. Here we see only 5. Typically, the first 3 trends are the LAB values. So you have the lightness, the red-green axis, and the yellow-blue axis. Here we see a delta E, and we see an opacity over here. Every measurement gives you a new bar. And the real advantage of the system is you see exactly at one glance how the color looks like. If you look at the last measurement over here, we are a little bit too light, a little bit too green, and a little bit too yellow. So even if you do not know which axis is what and how does it show, you see it immediately, too light, too green, too yellow. Here we were too dark, too red, too blue. So this is very easy to recognize where you are. We could also show here, of course, whiteness values, brightness values, UV included, UV excluded, whatever you like. And we can give you, this is very typical in the paper, in the white paper industry, we can give you 2 of these screens. For example, you have LAB, brightness, whiteness, and whatever, UV excluded, and the same windows again, UV included. Then you have really full information about your paper. So what we talked so far was about color measurement. Now I want to talk a little bit about the closed loop color control. Here I have again my paper machine. We make the measurement at the end. We transfer the data to a computer and we show here these bar graphs, which I showed you already. If we want to make a closed loop control, we know here where we are and we know where we want to be. So we do a calculation what needs to be changed. We send this signal up to our pumps kit and then we adjust the dye flow which goes in here. So this is this closed loop control. We get the measurement over here, go back to the beginning of the machine and adjust the flow of the dyes in here. I will show you this a little bit deeper in detail later on. So first of all, let's talk a little bit about the optical brightener, which is very special for the white paper industry. The optical brightening agent, OBA, is also called sometimes fluorescent whitening agent. It's a FWA, so both is the same. I normally say OBA. This is what I'm used to, but it's the same. What does it do? It switches on kind of blue lamp into the paper. So it transfers energy and it makes the paper a little bit bluisher. It absorbs the wavelengths below 420 nanometers, something like this. It's not always the same. And it transfers it to higher energies so that we have an emission at the blue range. If we look at the paper, so this is a bleached pulp. If we add in OBA, it looks like this. And just what I explained to you, what happens with the OBA, this energy here will be absorbed. So this is what the optical brightener does. It takes the energy from here, it absorbs it, transfers it to the visible range, and it emits the energy over here in the blue range. And the speciality is if you illuminate with 100% of light, you can even have reflectance curves above 100%. So this is what the optical brightener does, and this is really a specialty for white paper. The problem is if you add an OBA, you can increase the whiteness for a certain point. So the basic whiteness can be increased up to 70 points in CIE whiteness with the OBA. If you add more OBA, you even decrease the whiteness because the paper becomes greenish or yellowish, it depends how you say. So this is the problem. Sometimes if you want to make the paper more white and you add more optical brightener, you make it even worse because the whiteness will get reduced. So this can never happen with a closed loop color control. What makes it so difficult to do this by hand? This is what would be ideal. You'd have one die which reacts on the L-axis, you have one die which goes to the A-axis, and you have another die which goes to the B-axis. But in fact, this is not existing on the market. Each die influences all axes. You can imagine if you add a blue, it's getting darker. You will change the B value to the blue side, and if it's a reddish blue, you will be even more red. Same with the violet and same with the yellow. I put the yellow in brackets because most of the people who make white paper, they are using blue, violet, and an optical brightener. And the optical brightener makes it even worse because the optical brightener also influences all of the axes. And on top of that, you control the whiteness. So this is what makes everything very complicated. The closed loop control will really calculate how much you have to change each of these dyes to go to the right color. How can it help you to save money? So this is one thing which shows you what is the big value of the closed loop control system. If you make a paper, if you start up your machine, let's say, you have to make all these stuffs, you have to control the pulp flows, you have to adjust the width, you have to adjust the caliper, you have to adjust the chemistry, pH, really everything. Typically, paper makers need a certain time for that to adjust everything. And then when they have adjusted everything, they adjust the color. They do not do it in parallel because everything which you adjust here will change the color. Only the color will not influence any of these parameters. So they do it sequential. They set up the machine, and at the end, they adjust the color. So it takes a certain time until you have really sellable paper. If you have a closed loop color control, of course, we cannot influence this process. So this process is exactly the same. You have to do it, or the paper makers have to do it. You have to set up your machine. But at a certain stage, when the paper makers say, now we are nearly about to be on color, or we have set up all these parameters, they just press a button on the closed loop color control. And while they are still adjusting everything over here, the closed loop color control goes to the right color. And typically, if they are finished with their process, the color is finished as well. So that means this period over here, everything over here, helps you to produce more sellable paper, less waste. So this is the big advantage of the closed loop color control. You can do the color adjustments during you set up the machine by itself, just pressing one button. What do we need for this? Of course, if we talk about adjusting everything automatically, we need a continuous coloration. That means we need liquid dyes or liquid pigments. We have to pump them somehow into the system with different kind of pumps. So we can use any pumps you want, maybe even pumps you have already in your house. And the only question is we need somehow to give you a signal to adjust these pumps. If you do not have pumps, we can sell pumps. So we have also the possibility to give you the full system, including the pumps. We are quite open for that. The calibration samples for the closed loop control have not been done through you. We are working together with all the dye suppliers. They love us, they help us. They will give us the calibration data for the dyes you are using. So this makes your life quite easy in the paper mills. What is possible? So if you have 3 colorants and an optical brightener, we can always go to the right color of the paper. So we will control up to 3 colorants and the optical brightener at the same time, not in steps, one after the other. We calculate what needs to be adjusted and we go to the right color. Typically for white paper is that you only use a blue, a violet, and the OBA. Of course, also this is possible. If we have the right colorants, we can make a delta E, delta L, delta A, delta B, so in total a delta E of 0. So this is very easy. And if you have less than 3 colorants, or let's say OBA, then of course we can also control the color, but it just goes to a certain point. It does not have to be always 0 because this is physically impossible. And even here, the dye stuff supplier is responsible for the injection point. So sometimes you cannot inject the dyes or the colorant, the pigments and the optical brightener at the same spot. Sometimes this has to be at different places. Here we also work together with the dye suppliers. They should define where we have to add what. What are the advantages of the closed loop control? So of course it provides an on-time process correction, which means you have to do nothing. It goes in automatic mode. It minimizes all the times when you start up the machine, or if you have a shade change, if you go from one white to another white, including optical brightener, whatever, you just press a button. The color change will be done in automatic mode. Of course, all the other parameters need to be optimized from the paper makers. As you are more quick on your paper, on your cell-able paper, you have less off-spec production. During the run, the product uniformity is much better than you will do it manually, because even if you have a change in the raw materials, or if you bring in some waste from your machine from somewhere else, it will be automatically minimized by the closed loop control, so you will be right on color all the time. It optimizes your dye usage. You will have no overdyeing through OBA or through the pigments. It takes the guesswork out of this process. What does it mean? If you have an experienced paper maker who knows how to work with the pigments, with the OBA, he can only guess. He can say, I know we need more blue and we have to reduce the OBA, but how much? Increase the blue by 3%, 2%? Let's start with 1% and then we can go another step. So with this closed loop control, you can calculate it and you know exactly you need 2.8% increase of blue and reduce the OBA by 5.6%, whatever. During these shade change times or machine startup times, the operators can focus on all the other parameters which needs to be done. So they do not have to set up the machine properly and then start the color. They can do it, they just focus on their machine. At a certain point, they press the button and the color goes on automatically. So this saves a lot of time. And of course, it minimizes the need for tear out samples. You know when you are on color, you do not have to make a real change. Take a sample, bring it to the laboratory and confirm that you are on color. You immediately see it and you can start your production. How do we bring the dyes or the pigments, let's say, into the process? Normally, we say never inject concentrated pigments directly into the process, because if these pigments stick on certain fibers, you can have they call it a marble effect. So you have some fibers which are more colored than the other fibers. So a dilution is necessary, but we do not want to have pre-diluted dye stuffs. Why? If you get your dyes from your dye supplier, typically they have a good shelf lifetime. So if you take them as they are, they will survive for a long time. As soon as you dilute it, there could happen several problems. Either the pigments go down, or you have a precipitation, you have crystals inside, anything can happen. If you do this dilution manually, it's labor intense and there is a risk that somebody makes an error. Of course, all this stuff will then influence your color measurement or your color on the machine. If you have automatic dilution systems, they are really expensive. They cost even more than a full closed loop color control system. As I said, you have a precipitation in the pigments as soon as you dilute them with water, and you decrease your shelf lifetime. So the better way is use pumps which have a very small volume to pump the concentrated dye. This helps you to have the best available storage time of your tanks, and only at the very end we dilute the dyes with water and bring it in. I will show you a picture, next slide. If you have 30 liters per minute, which you bring into the system, you have a dilution of 1 to 1,800, which is by far enough. So with this system, you can avoid a marble effect. So it's diluted. All the fibers have the same color, which go onto the machine. You will have a very homogeneous color at the end. You can have, of course, different injection points. If you have anionic or cationic dyes, or if you bring in the pigments on a different place than you bring in the OBA, you need two separate lines, but also this is possible. And we do have many years of experience, and there are pumps available which have a maximum flow of a few milliliters per hour, up to 250 or even more liters per hour, of course. So dosing concentrated dyes is really not a problem. Next picture shows you how we normally do this. So let's say I have here just two colorants. So I have a blue, I have a violet, and I have an optical brightener. In this case, I put everything into the same pulp, the same injection point, but of course you can split it off. You can have two different injection points. So what we do is we have a tank somewhere and we have a pump, and the pump goes a long way up to the injection point. And at the injection point, we have one tube going into the pulp process, or in the pulp tube. And there we have approximately 30 liters of water per minute, which are feeded into your process. So if the dyes and the OBA come in here, they will be automatically diluted and go in here. But this hose has just approximately 20 inch of length. So there is not long time where the dyes or the OBA is in contact with the water. So it goes directly into the process. We do this typically right in front of the fan pump. So the fan pump mixes up everything quite well, and then it goes into the process. So this is how it looks like, and this is a very easy way to bring everything into the process and to have a good mixing and a very secure flow of the dyes, pigments, or OBA. So this typical application for this is if you have a white paper, which I said you have 3 pumps, 2 for tinting, 1 for optical brightener, or even 3 pumps for tinting. It depends what system you're using. It can be used for linerboard, for colored papers. This is very, very easy. The advantage is you have a minimum delay time, because if you add a little bit more dye from blue, let's say, it immediately is into the process. It doesn't take a long time to make this change happen. It's immediately in the process. The disadvantage is all the pipes are filled with concentrated dye. So that means if you really want to go through another dye, you have to change, you have to empty the tubes, but normally this doesn't happen too often. And you need, of course, several thin pipes, or we typically use hoses to go to the injection point. So how does it look like? This is a system where I show you how this could look like. So you can have an IBC, or typically you have just smaller tanks. So you have a tank over here. You have 2 filters over here. Why 2? You can, if you have valves over here, you can take one filter out, you can clean it while the system is running through the other filter. We have the dosing pump over here, and then we have here this injection point, as I shown you before. We recommend, of course, 2 valves over here if you want to change the pump. I would use 1 valve over here and over here. If you fill up the line, you close this valve over here, you open the valve over here, then you can start pumping until the dye goes over here, and when it drops out over here, you know that you are right in front of your injection point. It takes only a few more minutes until you are really into your pulp. So this is just for filling up. If the line is filled up, you leave it like it is. You do this for all the different dyes you have, and of course for the optical brightener. Then you have the hose, or the tube, which is going into your flow. If you shape it like this, it goes smoothly into the process, and it's very well mixed in this high density fan pump. So this is how it looks like. Now let's talk about different pump types. So we have a lot of experience with pumps. If you have a pump which you are already using, and if you are happy with this pump, we recommend you use it. We do not force you to change it. If it's working for you, it's working for the closed loop control as well. We are offering Brown-and-Lübbe pumps, for example. So this is the most expensive pumps, or these are the most expensive pumps which are, I think, on the market. But they have a very high range. So if you use these pumps, you see they have a range from typically 10,000 to 1. This is a very big advantage if you sometimes need a lot of volume, pump volume, and sometimes very little. They have two valves at the beginning and at the end, which could cause problems. We need here these pressure sustaining valves, because if the pump is higher, let's say, than the injection point, the dye could flow through the pump directly into the injection point, even when the pump is switched off. So this is the reason why we need pressure sustaining valves, and of course all these valves can somehow stuck or be blocked, so then the pump is not working correctly. But you see we have a very, very high dynamic range for the pump, so this is excellent. Another pump type are these Grundfos pumps. It's a peristaltic pump. It's a membrane pump. So it's the same principle, but here the pumps are much more cheaper. So it's just a few $1,000s. If you have a problem with the pump, it's very easy to exchange the whole pump. It's not a big deal. But they have only a range of 1,000 to 10. Brown-and-Lübbe was 1,000 to 1. Brown-and-Lübbe was 10,000 to 1. But it's basically a good pump, and if you do not need this high dynamic range, it's perfect for adding dyes to the process. And another system which I can recommend are peristaltic pumps. So these are Watson-Mallow pumps. It's quite nice because you have a hose, you can have different diameters, and for these they also have a high dynamic range. With one hose you have 2,200 to 1, which is even better than these Grundfos pumps, but not as good as the Brown-and-Lübbe pumps. The big advantage here is you do not have any valves, so they are quite insensitive to dirt. Even if you have a match or something like inside the tube, it just flows through. There is no problem, no stacking or whatever. And they are even self-sucking, so you do not have to fill up the line. You just start to pump and the dye goes through. So this is a very easy pump. This was just a short excursion for the pumps. Now I show you something about Lenzing. Lenzing is a company in Austria, and this is published. If you want, I can send you an article about this. Lenzing has basically, it's a little bit confusing, this diagram, but they have 4 lines of pulp. So they have here a line which is waste paper. They have envelopes over here, everything. This is a line where they have printing paper, so most likely white stuff. Here they have white non-printed clean waste, and they have fresh material virgin fibers. So the problem is they want to reduce, of course, the virgin fibers. They want to reduce this white stuff, and they want to use as much of these recycled material as possible. They had a goal to reach 63% of the total production should be made of waste. And they have several instruments. So one is over here. It looks like it's quite at the end, but honestly, they want to check how much colored material they bring in here. So they want to have here a quite stable production. If the forklift driver over here is told use a blue one, use a red one, so they sort their recycling material, then the forklift driver is told you use a blue bale, you use a red bale, and you use a green bale. If they see we are getting to greenish, then they say, okay, listen, use 2 red bales and the blue bale and not the green one. So this instrument over here shows the forklift driver how he can load his pulper to have a certain color over here. And you should know the time from here when he's loading the pulper until it's over here, it's approximately 20 minutes. The time from here until the end of the process is approximately 2 hours. So there are big tanks, big chests over here to store everything, so they mix it up again. This is a kind of pre-warning system for the man on the machine. If he says that if he sees that the color is changing dramatically, he can change the flow of these two lines to have more fresh, uncolored material that the machine is already set up over here. And then he has one more instrument at the end of the machine to control the paper, the color of the paper. So Lansing said in an article, they did it, of course, to maximize the waste usage. They have shortened the transition times. Before it was 30 to 50 minutes. So when they do a manually transition, they took 30 to 50 minutes. And after installing it, it took only 15 to 20 minutes. So you see, you can reduce these times by 50%. The load relieving of the operators during these changing periods was much less. They had to take samples before from the running production machine, go to the laboratory and check whether the color is correct or not. Now they rely to 100% on the color measurement, which is quite easy for them. They have tighter production tolerances as they had before. And I always ask the companies, can you tell me something about the return on investment time? And this is always difficult to get real facts. But the person told me, you can be sure that every instrument had a very short payback time. This is the reason why we bought another and another instrument. So I was really happy about this. And by the way, yeah, so this is really nice. These are some facts which are also on our homepage. We have here customers which made a statement which we were allowed to publish. So this is Leipa Schrobenhausen in Germany. Mr. Kaltenecker, he is now the plant manager of Leipa. He said after startup of the system, the advantages that had been expected were realized soon. Reduction of waste during grade change by 25 to 50%. So this is a fact. And he said also that he trusted in our know-how, and this helped him to go very quick to the right color, to install this closed loop control quickly, let's say. This is another statement from Mondi Laubling in Germany, Mr. Oliver Ciric, he's the technical director, and he said that with the closed loop color control, so they make brown paper, I have to say, and they have really dirty waste. There goes in everything which comes on the waste paper side. So they can achieve delta E values from 0.1 to 0.2, which is perfect. And only little maintenance effort required. And the last one is from Arctic Paper. Since we started using the inline closed loop color control from X-Rite, we have no more complaints about color from our customers. Perfect. Let me tell you at the end something about how we install the system. So typically we need for a closed loop control system 4 days to install. On the first day, we need a shutdown of 2 hours of the machine, where we install the frame mechanically. So we go there, we bring our frame with us, which is customized for this machine. So we have to mount it into the machine. Then the machine can start up again. The rest of the installation is done while the machine is running. So at the end of the first day, we typically have a color measurement on the machine and we let it run overnight. Second day is used to install the closed loop color control, so typically the pumps. It depends how quick we are. If we are confident at the end of day 2 that the closed loop control will do its job, we will let it run overnight, and we only train the night shift to show them what should they do if something happens. So if the color goes off spec or whatever, if they have a problem, how to switch it off and how to switch to a manual mode. If not, we just let the measurement run, and on the third day we do the training, real training on the closed loop color control. So for sure, day 3 to day 4 in the night, the closed loop control runs in automatic mode. We have trained typically 3 shifts. And at day 4, we are only there for fine tuning. If something happens or if there needs to be something a little bit better adjusted to be much more quicker on color, this is what we do on the 4th day. If we talk about how much does it cost to have this system, every 2 weeks or every 6 weeks typically, we recommend the operators or the maintenance people typically to check the system, to make an external calibration and to clean it from outside. Not everybody does it, but yeah. So this takes maximum 30 minutes. Most of the time, takes it to get a white standard from somewhere from the laboratory, go to the machine. The calibration itself lasts 30 seconds and then to bring it back. Once a year, we recommend to have a service technician on site. He is doing the cleaning of the instrument. He is coaching engineers or whatever you have there to use it the right way. And he gives you at the end a certificate. All of our instruments are long-term investments. So we have an instrument from 1990, so which we sold 1990, and this is still in operation. Unfortunately for us, but this is how we want to have it. We do not want to have a system which fails after 5 years or something like this. The system has a very high availability, so typically it's by far above 99%. And as I already mentioned before, we have many happy customers. That means if you know somebody using our system, just ask. Everybody will give you a good recommendation about the X-Rite color measurement and closed loop control. If you need more information, you can contact this homepage, www.erx50.com. Here you find everything about inline color measurement from X-Rite. So this is everything from my side. Thank you very much. Are there any questions?
Yeah, if anyone has any questions at this time, feel free to submit one. So a few minutes left. It looks like there are no questions, so we'll just end the webinar here. For everyone that has joined, you'll receive an email with a link to this recording. Thanks for joining and have a great day.
Thank you very much, everybody.